So we're going to do 2D and 2E. We've got sine 2x plus 2. Oh, didn't we do something with that one? I think we did a like second derivative thing with that. But all right. But here we're going to do the full meal deal. So we're given some info. So apparently the sine of x is negative a quarter. It's going to come in handy at some point, as will those two values. Okay. So keep that in mind, or keep the sheet handy. You're working off of my paper now, some of you. Or your own paper. All right, what was it? It was y is equal to, have your formula sheet handy as well, right? When you start seeing stuff like sine 2x, 2 cos x, 2 cos x. And our domain is given to us. And it is 0 to pi. Okay, intercepts. Intercepts. Well, let's do the y-intercept first, right? Easy one. So set x equal to 0. And what's that going to give us? Y is equal to sine 0 plus 2 cos 0. Actually, finish cos. All right, what's sine 0 plus 2 cos 0? What's sine 0? Let's start with the easy one. 0. What's cos 0? 1. What's 0 plus 2 times 1? 2. Okay. Y equals 2. So we have 0, 2 is the y-intercept. X-intercept. Set y equal to 0. So what do we got now? Let's do it the other way. So sine, go under, sine 2x plus 2 cos x is 0. All right, can we do this? Well, sine 2x could be 2 sine x cos x, right? Well, not could be, is also 2 sine x. Oh, that's kind of handy, right? Because now we got like 2 cos x's in both terms, so we can factor out a 2 cos x. 2 cos x. And what do we get? Sine x plus 1. Easy peasy. So 2 cos x is equal to 0. 2 cos x is 0. And in the domain 0 to 2 pi, what's x? Pi over 2 and 3 pi over 2, you say? Correct. And this will be sine x plus 1 is 0, so sine x is negative 1. What's that, you say? We already have that. It's 3 pi over 2. Oh, so we do. All right. Yeah, we can do a little bit of a sketch now, right? We could start going 0 to 2 pi. Let's say that's pi over 2, 3 pi over 2, 2 pi. 3 pi over 2, pi over 2. 0, let's call that 2, negative 2. Hopefully we won't have to rescale anything. What was our little hints? We got to keep 1.45 and negative 1.45 handy, apparently. But that's okay. Those are within spec. So what did we have? This was an intercept. Pi over 2, 3 pi over 2. All right. There we go. Keep on. Okay. Good on intercepts. C. Let's see. Symmetry. So there actually is symmetry here, and it's a type of symmetry we haven't looked at, but it'll happen in trig functions. And that is that we could say the function, which is g of x, not one, g of x. So that function, you notice, what do we got? We got sine 2x and 2 cos x. So sine 2x, the period of that is pi, and then 2 cos x, period of that's 2 pi. So the period of the whole thing is going to end up being 2 pi. So what we can say, you're not responsible for this. But g of x plus 2 pi will be equal to g of x. Okay, and that'll be true for this function, right? Because the period's 2 pi. So if we did have to draw more than this, we could just draw 0 to 2 pi and then slide the whole thing over 2 pi to the left. That's your right, 2 pi to the right. And slide the whole thing over 2 pi to the left, and so on, right? So it's periodic symmetry, right? Every period, so the period being 2 pi, every period will be the same. So in this trig function, and you're not responsible for this, but you might see it in the future. So trig function, in this trig function, we have periodic symmetry. Right, and that one period will be the exact same as another period, and so on. Right, so we could just translate the graph if we had to go beyond. Right? We could just translate the graph. Translate the graph. Multiples of 2 pi. Multiples of 2 pi. Who knows? Maybe next year you run into this stuff. Right, or later this year, September-ish. Asymptotes. Any asymptotes? Just a basic trig function, right? So, and it's not tan, it's just sine and cos. So, asymptotes. There will be none. Right, and there's no denominator. There's no secant, cosecant, tangent, cotangent. There's no denominator. There's no asymptotes. Intervals of increase and decrease. So, what do we need first? The first derivative. The first derivative. All right. What was it? Sine? What was that? What function? Sine 2x. So that's just going to be like 2 cos 2x, right? 2 cos 2x. And then, what do we have? 2 cos x. So minus 2 sine x. Did that? Oh, yeah, we did this, but we were just interested in the second derivative, right? So from there, the second derivative is pretty easy, and we will be doing the second derivative again. But here we're looking for intervals of increase and decrease, so we got some work to do, right? We gotta get this into a factored form. Find the zero. So this will be defined everywhere, right? I mean, it's just a trig function, and there's no denominators, no zeros in the denominator in it. So cos 2x, what can you become? You become 3 things. Cos squared minus sine squared. No, that wouldn't be that good. 2 cos squared. No. 1 minus 2 sine squared. That might be useful. Right? Because 1 minus 2 sine squared would just mean everything would be in terms of sine x. So 1 minus 2 sine squared x minus 2 sine x. All right, let's expand. Let's factor and rewrite. Let's pull a negative 2 out. I want that to disappear into the equal sign. Negative 2. So that'll give us what? 2 sine squared x plus sine x minus 1. Okay, check that, make sure it's right. Good. Does the quadratic binomial? No, it's quadratic. Does the quadratic factor? Well, if it does, what's it going to be? Plus 1 minus 1? Does that work? 2 sine squared plus 2 minus 1 is plus 1 minus that. Nice, nice. So this is defined everywhere. G prime of x is defined everywhere. Right? Remember, critical space here. G prime of x is defined everywhere. Everywhere. And G prime of x equals 0 means 2 sine x minus 1 is equal to 0, so sine x is 1/2. So x is pi by 6, 5 pi by 6. Come back to me now. That second derivative thing was at pi by 6, right? It was like show there's a maximum. We know where this is going. We're going to end up with a maximum here. And what else do we got? Sine x plus 1 equals 0. Sine x is negative 1. X is 3 pi by 2. That was one of our intercepts. All right, well, let's scooch back up to the top. You may arrange this any way you like under. Oh wait, we didn't say it. Oh no, we haven't done the intervals yet. Wait, so sorry, we're not on F. We're still on E. We need to take. It's going to start at 0. It's going to end at 2 pi. And what do we got? Pi by 6. 5 pi by 6. 3 pi by 2. The north wind. Good morning. I walk into the damn wind every morning. Why? One of the other math teacher walks. She lives north. She's got the wind in her back. And by the afternoon, it's usually reasonably calm out, I think. Not fair. Okay, we need factors, right? What do we got? -2. So very important, right? This time I kept throwing down like 2's, right? You go plus, 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 plus. Really important though, because it's the -2. So that is definitely going to have an effect. Right? So you don't ever want to forget one of, just a constant factor. So well, we're looking for zeros. All right, so what do we got? 2 sine x minus 1. 2 sine x minus 1. And sine x plus 1. Let me know if I messed up. G prime of x is going to have a certain sign, which will lead to g of x being whatever, increase or decrease, right? So -2, that's negative. Two sine x minus 1. 2 sine x minus 1. So, well, the critical numbers are the half, right? When it's a half. So at pi over 6, it's going to be 0. So until then, it's climbing up and getting to a half. So it's not big enough to be positive. So it'll be negative here, right? Then it's going to be over a half, right? So when it's hit 1, like at pi over 2, that'll hit 1. And then sine pi over 2 is 1. 2 times 1 is 2 minus 1. So the minus here plus here, right? And then at 5 pi over 6, it's going to drop below a half, and then it's just going to go negative. for the rest of the way. So there we go. See if you agree. And sine x plus 1, well, the lowest sine x can go is -1. So if we add 1 to it, then the lowest value we're going to get is 0. And that's going to happen forever. So it's just going to be pluses all around. Okay. Does it make sense? So g prime of x, what do we got? We got a plus. We got a minus. We got a plus. And another plus. So that is increasing. It is decreasing. It is increasing. It is increasing. So probably a point of inflection. Right? We're just going from increasing to increasing, but there's something going on. The first derivative is 0 at that point, right? Okay, so we do it. Oh, well, there's a max at pi over 6. How surprising. But we got to state intervals of increase and decrease. So g of x is increasing from 0. And remember, 0 is our hard cap. Left side, right? To pi over 6. And 5 pi over 6. To, okay, so we know this is continuous, right? We know the function is continuous. Because something's happening here, but it could be an asymptote. Right? It could be a hole in the graph. Now we know it's not. So what's happening here is more than likely a point of inflection. And we'll show that when we do the second derivative. But in that case, because I know the function is continuous, then I'm just going to say it's increasing from 5 pi over 6 to 2 pi. Otherwise, I'd have to split the interval. Right? So if we knew if there was an asymptote there, then we would have to split this interval and say 5 pi over 6 to 3 pi over 2, u 3 pi over 2 to 2 pi. But it's continuous, so it's going to increase from 5 pi over 6 straight up to 2 pi. And is decreasing, where? Pi over 6, 5 pi over 6. Okay. And that's it. Okay, so far so good. F. Intervals of increase and decrease. Now, if you write these down each time, so every time you do it, if you go A, domain, blah, B, you know, this. Oh. We just did that, didn't we? See, if you write these down each time, you'll come to know. Apparently not. Never mind. Forget it. F. Where it's on here. Local max and local. If you write these down each time correctly, just keep that sheet handy, right? It's got local. And it's in the textbook too. Local max and min. You'll at least be familiar. We don't expect you to memorize this, okay? So I'm pretty sure. I haven't seen the test for like 2 years now. But if I remember correctly, it's basically going to guide you through a curve sketch. Just ask, you know, number 1, what is the domain? Number 2, what are the intercepts? Number 3, blah, blah. All right, so where are they? Oh, what have we got? Well, we know. Right, we can see. We have a local max at pi over 6. We knew that. We did that the other day. Local max. X equals pi over 6. What else? Be a local min at 5 pi over 6. Well, let's do the local max. So g of pi over 6 is, oh God, where is it? sine 2x, sine, okay if I just go sine pi by 3? Sine 2x, right? Plus 2 cos, plus 2 cos pi by 6. Right, work it out, see how good your mental image of the unit circle is. I don't have one, but I just know the numbers. So cos pi by 6 is root 3 over 2, but it's better not to cancel the 2's, right? You might just say, oh, it's 2 times root 3 over 2, which is root 3, in which point you got to get the common denominator back. So, a little chess move, look ahead one move. Say, no, let's just leave it as 2 root 3 over 2, because I'm going to have to add those. So we got a local max at pi by 6. Pi by 6. 3 root 3 over 2. They give us that value? No. Seems a little negligent. All right, what's root 3? So it's like 1.7 times 3 is like 5.4 divided by 2 is like 2.7. We'll ballpark it. Pi by 6. So, where's pi by 6 here? 1 pi by 6. 3 pi by 6. 5 pi by 6. That, so where are we? Over here, 3 root 3 over 2. There's our max. Okay, got a local min. Local min. 5 pi by 6. G. 5 pi by 6. So it'd be the sine of 5 pi by 3 plus 2 cos 5 pi by 6. All right, now pi by 3 and 5 pi by 3 have the same reference angle, so it's still root 3 over 2, but it's 5 pi by 3, so it's in quadrant whatever, so it's negative. Quadrant 2, and that's in quadrant 3, sorry, that's in quadrant 2, so it's negative, but it's still, so negative 3 root 3, negative 3 root 3 over 2. So 5 pi by 6, negative 3 root 3 over 2. Oops, I didn't sketch that. Formally. Then there's a negative 3 root 3. Okay. 5. There we go. And you can make the decision for yourself. Do I want to kind of sketch it out as I find stuff, or do you just want to wait till the end? I don't know if there's a right answer there. G, concavity and POI. You notice how intervals of increase and decrease and max and min are separate, but concavity and point of inflection, which should really be separate. There. I didn't make it up. I think it's inconsistent. Okay, second derivative. Handily, the first derivative's here. Also, if you flip back a few pages in your notes, you probably have the second. But what's it going to be? So 2 times 2 will be 4, but then it's cos, so it'll be minus. Minus 4 sine 2x minus 2 cos. Now we didn't do anything with that, right? Second derivative test, we were just told, hey, there's a max of pi over 6. You know, show that it is. And so we showed the second derivative was positive. But this time we have to go through and factor this, right? So sine 2x is going to become 2 sine x cos x. 2 sine x cos x. Cos x minus 2 cos x. So we can pull a 2 cos x out. Or we can pull a negative 2 cos x out. If we pull the negative out, let's leave this with a positive. So let's pull a negative 2 cos x. So that'll become positive 8. This will, and cos 2x. Cos 2x. This will flip signs. And so become a 1. And this will flip signs. Become minus sin x. So 8 cos 2x, 1 minus sin x. Mess that up. What did I look at? Right. That's like that, right? So, see? Having the rack wrong. Okay, let's try that again. So we have the 2. Okay, so we take a negative 2 out, negative 2 cos x. And that'll be 1 for that, and that'll be, okay, that's already got the 2, so that's going to be plus 4, yeah, plus 4 sine. Okay, how's that? The negative 2 cos x, I'm going to have a negative 8. So, yeah, that works, right? Okay. So that'll be defined everywhere. When is it 0? Oh, see, now that's why they gave us the sine negative 1/4, right? Sine x is negative 1/4. Okay, so no room up there. We'll just continue down here. G, continued. Okay, so what do we want? Negative 2 cos x bracket 1 plus 4 sine x. So we want that to be 0, which means negative 2 cos x is 0, and x is, anyone? Pi by 2 and 3 pi by 2. And 1 plus 4 sine x is 0, 4 sine x is negative 1, sine x is negative 1/4. And on the sheet, what does it say? 3.394. Uh, 3.394, and 6.031. Plus 2n pi, and n belongs to the z's. Somebody snuck out an IB and snuck that in there. We would say belongs to the integers, but in another math language speak, z is the set of integers. Those of you former IBs will recognize that. And you never know what you're going to get, right? Whatever textbook you're using. Okay, what do we got? What do we got? We got 0, we got a pi over 2. We got 3.39, so that's just a smidge over pi, so that's probably going to come next. 3.394. Then 3 pi over 2 is what? 9 divided by, that's like 4 something, right? So that'll come next. And 2 pi, which is 6.28, and so 6.031 comes there. And we have, what do we got? Negative 2. Negative, 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 negative. Cos x. And 1 plus 4 sine x. Put them all together. You get g double prime of x, which gives us information about g of x. All right, so fill them in. Well, cos x is positive in the first quadrant, and then after that it becomes negative. And then we get into the fourth quadrant, so it'll be positive again after 3 pi over 2. So from 0 to pi over 2, quadrant 1, cos is positive, then it stays negative till 3 pi over 2. 1 plus 4 sine x. Well, the first quadrant is positive. In the second quadrant, it's positive. That goes a little beyond the second quadrant, but then that goes a little beyond 0, right? So then that'll still be positive. At which point, it's going to hit into quadrant 3 and be below negative quarter. So that'll be negative, and it'll stay negative, and it'll stay negative. Oh, wait, stay negative? No, because at this point, it's going to be the negative 1/4 again. So in this little smidge, right, which is just the last little bit, it'll hit the 6.031 where it'll be 0, and then it'll go positive. Just that little chunk into Q3 down to 3.394, and then that little chunk of Q4. So what do we get? Negative, positive, negative, positive, negative, CD, CU, CD, CU, CD. What's that? 1, 2, 3, 4. There's 4 points of inflection. But first, so g of x is concave up. You may use CU. I will not take any, like no diploma in this. Nobody's taking marks off. But be aware, it's a little more formal type thing. You might want to write the whole word concave up. Pi by 2 to 3.394. And 3 pi by 2 to 6.031. G of x is concave down. Concave down. Where? 0. I'm going to check out. I'm not sure if that should be a square bracket or a round bracket. I mean, it's a hard limit. 0 to pi by 2. 3.394 to 3 pi by 2. And 6.031 to pi. Asterisk, 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 asterisk. So at the asterisks, there are points of inflection. But we've already got values for some of those, right? Pi by 2, 3 pi by 2, those intercepts. Whoops. There, pi by 2, 3 pi by 2. Okay. So they're points of inflection. What else? So we got 3.394. Okay, pi by 2, 0. 3 pi by 2, 0. 3.394. And they should tell us then, right? Which they did. Negative 1.45. And 6.031. Positive 1.45. And that should be it. Put those. Okay. So 3.394. That's going to be like about here. And put a little asterisk. Let's go 3.394. And 6.01 will be about there. Okay, and then what did we say? The positive, well, wait, this one has to be down here, right? Yeah, 3.394 is negative 1.45. Hang on, let's get that. Negative 1.45, 1.45. Okay, negative. I put it the wrong track. Here. And this guy will be a positive 1.45. Okay. What up? That's it, right? Like, what up? Okay, so we've just got our concavity. Increase, decrease. You know, it has to be increasing here, right? And it's going to have to be concave down. Is it in the first interval or is it concave down? Yep, first interval is concave down and increasing. Right? Now we have concave up and decreasing. No, what concave? Where's it called? To here. That's our point of inflection. Then it becomes concave up. Then it becomes concave down. Wow, you're messing this up here. Then it becomes concave up. Concave down here, and then concave up. And then at 2 pi, it's going to end up back at 0, or 2. And it's going to start to be concave down. And it's actually going to hit another piece up there. And repeat. That. Try and draw that better. I did. That's not good. It's a bit messy. Let's go look. So there's our graph, which we were doing from here. Here to 2 pi. So here. Well, actually, like exactly. Okay, I can't write up exactly there. All right. Can't draw. What's next? Can't move. Oh, there it goes. All right, hang on. Go down. All right, go down. All right, what do we got? Who are you? You are H of X. And this is E, 2E. H of X. I say that in honor of season 6 of Line of Duty is now releasing in Britain. Got to say your H's. 1x squared. what do we got here? So apparently we need to know that the root of x is ln x has no solution, and that the negative root of x equals ln x is true when x is about 0.49. All right, put that away somewhere. We'll need it in a bit, I guess. What's our domain? A. So it's going to be dependent on what? X? Ln x? Ln x, right? So where's ln x defined? So 0, not including 0, to infinity. What's next? Intercepts. Intercepts. So y-intercept, set x equal to 0. We can't. None. So there cannot be a y-intercept. We can't make x 0. X-intercept. Set y equal to 0. What do we got? X minus the ln of x quantity squared equals 0. Well, then x is going to equal ln x squared. So now what? Oh, maybe that's why they had the root x. We're going to unsquare this. What's the left side going to be? Plus or minus root x. Right? So remember the plus or minus. Plus or minus root x. Now, what did they say? They said something. Yeah, root x equals, so we'd have to split this up, right? We're going to have to solve two things. Root x equals ln x, right? We're going to say, well, there's no solution. And negative root x equals ln x, which says x is about, it's like, really? You couldn't just say it's about 0.5? You know, draw a half on your thing and then just make sure that you're 1/100th of a unit to the left of it. Whatever. Should be accurate if you can. What's next? Symmetry. Well, there can't be. There can't be because it only exists on the one side. Symmetry. None. Asymptotes. So vertical. Well, it's a ln. There's a ln in there, right? So then we should perhaps let's take a look. So as we approach 0 from the right, what are we going to get? What's it going to be? You could just say what it is. What is it? So it's going to be equal to, but what's the limit going to be? Negative infinity. Why negative infinity? Small, yeah, so the x will be a small positive, okay? And then we're minusing what? What's ln x? Excuse me. You might have the right answer, you might have the wrong reason, I don't know. But, okay, so x is going to be 0, right? We'll say 0 minus, so ln x, so as we approach 0 from the right, ln x is going to be what? It's going to be negative infinity. But then we're going to square it, so now it's going to be positive. But we're subtracting it, so it's 0 minus positive infinity, which is negative infinity. So it is negative infinity. And I mean, if your reasoning was incorrect and you still nobody's questioning it, right? You wrote negative infinity, it is negative infinity, we're good. Okay, everybody clear on why? Because ln x looks like that, right? So as x approaches 0 from the right, ln x is going to be negative infinity, but it's being squared, so now it's positive, and then we're taking it away from 0, so 0 minus. So it's negative. Intervals of increase and decrease. What do we need? Our formula sheet, because nobody remembers. What's the derivative of ln x? 1 over x. Good. Somebody remembers. Okay, what's the derivative of h of x? What is h of x? So it's x minus ln squared. Let's write out h of x. It disappeared. H of x is x minus ln x quantity squared. So that's h prime of x. 1 minus 2 ln x times 1 over x. 1 minus 2 ln x over x. Or you might see it written x minus 2 ln x all over x. Right? So can we leave it like that? I think we can leave it like that. Right? I mean, our idea really is now to find out, well, so is this ever going to be 0? No. Because for that to be 0, what would have to happen? 2 ln x over x would have to be 1. Right, here, let's go scribble. So 2 ln, so for that to be 0, so 1 minus 2 ln x over x equals 0. So 2 ln x over x is 1. So 2 ln x would have to equal x. Is that ever going to happen? So think about the ln function. It looks like that. And then think about y equals x, which looks like that. And y equals x is always going to be above that, right? Because lns are pretty small. Like logs, they don't climb fast. These are never going to be. And I mean, here that's 0. That's all negative stuff. That's 1. If we make x e, right, like about 3, then this is going to be 1. Right? And like there's e sitting up there. So yeah, it's never going to happen. So there are no critical numbers. No critical numbers. Which means we just need to figure out the sign of this thing. Is it positive or is it negative? One minus 2 ln x over x. So 2 ln x is always going to be smaller than x, right? So this is always just going to be a fraction. And even if the x is negative, it would just be 1 minus, which would become plus, and then otherwise this is smaller. So this will be always what? This is always less than 1, right? So this is always positive. So h prime of x is always positive. So h of x is increasing from 0 to infinity. It's just kind of like the ln function, right? It's always increasing. It's an increasing function. So there can't be any local min or max, right? There's no lots of paper. Local min max. Local max min. Max min. None. G. Concavity. That's less complicated than the sine one, right? Concavity and POI. So what did we have? H prime of x. What do we say it was? 1 minus 2 ln x over x. Okay, do H double prime. I will pump. For those of you just joining us back again, I've been informed the recording stopped. I'm pretty sure we had done this. If not, take a look. And now we're looking where H double prime of x is 0, so we've got 2 ln x minus 1 over x squared is 0. Multiplied by x squared, divide both sides by 2. Ln x minus 1 is 0. Ln x is 1. E to the power of 1 is x. And now we're going to go for a little chart here. And we'll get h double prime of x. The sign of that, which will tell us. So that's minus, that's plus, that's concave down, that's concave up. We got a POI of E. What is this POI? Oh, where's the original function? X minus 1 squared x. So POI when x equals E, HE is E minus ln E quantity squared, which will be E minus 1. Okay, so point of inflection, E minus 1. Right, what else did we have? What was that point? So 0.049 was the x-intercept? Yeah, that was the x-intercept. All right, let's sketch. Okay, don't need much over there. So we got 0.49. We're going to need an E. So that's E. Let's say that's E minus 1. There, that's a point of inflection. It comes from there, we'll concave down, turning to concave up. Still drawing that as concave down. Concave down. It probably doesn't climb that fast. And what's it going to be? What is it? X minus ln x. X minus ln x squared. There we go. Or E. And then that would be E minus 1, like 1.78, 1.8. There's your 0.49. 5, apparently. It should have been 0.5, but who knows? We don't know what it was exactly. All right, now we're done.